Hi, Menas Kafatos. Long time.
Hi,
Actually,
hi
not
Sky.
long. I think we saw each other this summer, last summer,
That's right. We saw each other in Greece, right?
yeah, in Athens.
Right.
Okay. Um, so we first met in 2000, in, in early 2022, I think.
Correct.
Yeah, yeah. And
Of
the
course, we have been.
thing
I
was,
have been following you for a longer time than that, right?
yeah, yeah, yeah. Gina, you wanted to introduce us, wasn't quite successful, so I approached you by myself.
Right.
And it took some years for us to talk more and actually meet. Yeah, and the first meeting was uh, it encouraged me to find more evidence for the gravity part of my theory, because at the time I met you, I only had this data from Fishbach, and at that time I didn't know that the differences in gravity that Fishbach was looking at were minuscule, were like a billionth instead of a thousandth, which would be the natural order of magnitude for those ratios. Um, and some experiments I did in 2020, but those were not of so high accuracy. So then I
Correct.
went and analyzed the all the G measurements, all the measurements of G from the last 200 years, or mostly last 100 years. Yeah.
Correct. So, yeah, tell me a little bit more about the work you're doing now and the next steps.
Yeah, I got three different types of setups for free fall experiments. The very first one was using a clamp, and so in that experiment, one can only expect there to be uncertainty because of delays, and the data is spread out because of delays in the release of the ball, and it's registered through electricity. And luckily, while lead is not magnetic, but it conducts electricity enough, and so I could use lead balls and steel balls. And so, but then I had to always use the minimal value, and for that you can't really have you can have standard deviations, or at least not normal standard deviations. Okay, sometimes I will just list the current minimal value for each trial, which will be the same like 10 times, and then it might change, and then of that design. But that's something very curious. But normally,
Right.
you want to have an average, and from that standard deviations. So then I got two laser gates, um, and then you can use the average again, because then you're not concerned with when exactly it's released. You just care about when it
Right.
traverses the distance. But I still got quite a bit of spread in the data, and then I got a magnetic free fall adapter. It's over there.
Okay.
Yeah,
Yeah.
and yeah, this is extremely precise, and it has very tiny standard deviations. But today I also noticed that actually how large the spread in the data is depends also on how heavy the balls are. If they are very light, then tiny currents of air will change the free fall time. And I used the heaviest ball I could find and measured many times, and the spread in the data was only 0.3 milliseconds. So basically, the standard deviations was just 0.1 milliseconds, which is exactly the resolution of my measurement device, like
Right.
extremely tiny. And but it's to be expected, because the the volume grows faster than the surface area, and the surface area is what stops the air.
Right.
And so, yeah,
So that was my question.
the heaviest also have.
Yeah, that was my question. How do you get around that problem because that could affect the results, right?
I mean, the air resistance. Well, I have spheres with. So I have this vending
Hmm.
machine balls, and I put different. This is a lead, a lot of lead spheres in them, and this is steel, and
Hmm.
I make them weigh exactly the same. But well, exactly the same is not possible. So, uh, since there will always be a tiny difference, I make it so that steel, which is supposed to fall faster, I make it ever so slightly lighter, so that nobody can say, "Oh, it fell faster because it's heavier." And on top of them, I have this washers, steel washers, where I suspend them from the magnet. And I also tried putting the washers directly on steel spheres and lead spheres, in which I had drilled a lot of holes in them. But it's not so good because then the steel will stick much more because it's the washer plus the steel sphere, so there's even more magnetism. But when using these vending machine balls, this problem doesn't exist.
Okay. So where are you now? What have you concluded so far?
So far, with the best results I got with the heaviest spheres, and I wasn't even paying attention to that. I just used very heavy spheres, and the standard deviations were very small. It's only today that I noticed how much more it spreads out with smaller balls. Well, I did 20 trials with the new setup with new freefall adapter, and I got separate standard deviations for the median. You know, the standard deviations for the median. It's called MAD,
Okay.
and then there's and I made up standard deviations for the mode, like the most common value, and for the minimum, and so in all of those I get separate standard deviations. Like two materials are not overlapping at all, and that's what you would want to get, right? In cosmology, they talk about the trouble with Hubble because the two ways to measure the age of the universe, their standard deviations are totally separate, and so that then it's a real
Right. Right.
and so I thought about changing the setup, but then the standard deviations that I have for the only place which is not yet satisfying is I don't have separate standard deviations for the average, but I almost have them. It's like the time difference is 0.3 milliseconds, exactly what I predict, and I get that in the minimum, and in the mode it's a bit larger. In the minimum it's 0.3 milliseconds, and in the median, not so sure. Anyway, for the average I also get 0.3 milliseconds of time difference between the two materials. But the problem is that the standard deviations are also around that, but they are shrinking.
Right.
So if I don't get a lot of outliners, then they will continue to shrink. Actually, in the 20 trials, they only grew back a little bit in the 16th and 17th trial. So if I do it like 30 times or 40 times, I should get separate standard deviations.
Yeah, I was going to suggest that the best thing for you to do is to carry out the experiment many, many times
Mm.
and see the trend. Um,
Well, I already carried it out like 500 times, maybe all in all. And so my confidence in, I do see that in every experiment I do, there is the material that I predict to fall faster falls faster in the majority of the trials. In the experiment I did yesterday, for example, 9 out of 10 times steel was faster.
so I would say that since you now have a better experimental setup, the previous measurements don't really count very much. I would start with the new
Mm.
with the new way you're doing it, and rely more on that rather than you already have some indication from previous experiments. But I think in terms of achieving the results you want to achieve, you probably want to have a consistent, good setup that you now have
Mm.
and carry out the experiment many times.
In terms of having separate standard deviations, I had that without problem yesterday,
Okay.
and that was that was when 9 of 10 trials always steel was faster, which also before it was quite common, but having separate standard deviations was something new. And well, but then the time difference was more than I predicted, because the spread in the data was still considerable, but yeah, the standard deviations were separate, but sometimes they were overlapping, then separate again, overlapping, separate again. Yeah.
Okay.
So not totally separate, but pretty good already.
Okay. So that's good. So let's talk a little bit about the implications from the point of view of theory, or yeah.
Yeah, the implications would be that in theory you could do the opposite of what happens in chemistry. You could, like in chemistry, you have iron and there's a lot of negative binding energy, reducing the mass, because mass is a type of energy, a form of energy, but not reducing the number of particles. And so then you have more particles per kilogram, and so you have, according to me, more gravity per kilogram, because gravity depends on the number of baryons. And then you can do the opposite by inflating the mass. You could, using particle accelerators or some type of particle accelerators, one could increase the mass without increasing the number of particles, and then you would have very few particles per kilogram. But this is very difficult to do. You would have to find the densest gas that exists in the world, and then at least at the beginning, the tube mass and the mass of the gas should be the same, and then you inflate the mass of the gas. And
I see.
but then with you would have to use a Wakefield accelerator, which would be an accelerator where particles are accelerated using a laser instead of magnets, so there would be no magnets. And this has been done with normal air in hollow core fiber wires, but not with anything else. And
where was this done? Where was it this?
I have it cited in my book.
Okay, all right.
Not
In the book, okay, all right, that's fine. So I think it's what you bring it forward is very, very interesting from the point of view of theory, and at least it's worth for you to get as tight um, results, experimental results based on your improved experimental setup, and get the results out. And as it's done in science, as you know, let people try to shoot it down.
Yeah.
You know,
Well, I should emphasize that these experiments that I'm doing now are not really necessary as evidence, because there's already infinite amount of evidence in terms of G values in the historic data from big G. So there, according to my own calculations, the chance that this is a statistical fluke is just 1 in 10 to the power of 18.
I
So
see.
be far beyond
Right.
far beyond sigma 5. Yeah, but I always try to do more, and doing my own experiments is better than it's fun also. Yeah.
Right.
And
That's great.
you hear about Giorgio Toro. He made experiments with the pendulum, and he did 4 materials: iron, copper, aluminum, and lead, and they were exactly in the predicted order. The fastest swinging was steel, then copper, then aluminum, and then lead, exactly as I would predict. And the ratio was also agreeing to 99.97%, from that to 99.99%.
Did he publish the results?
No, that's the results of a friend of mine, but he didn't know at all what to expect, and so he wasn't impressed by that because he's not a theoretician. He just
I
wanted
see.
to test it, and so, oh, that's so small, it's not interesting. Like, to him, it's not interesting. And I said, no, that's exactly how small it should be. And 1,000th of a difference is not really small. It's pretty big.
Yeah. Good. So you will continue
Mm.
the experiments, and you will
And
keep it.
I also want to do experiments with scales and balances. So in theory, one should get a difference between a scale and a balance. And yeah, so I'm soon going to buy a very precise balance, because all these here, they're the scale here, that it's very precise, but it's still, it says balance, but it's not a balance. It's
I
such a
see.
up with scales and balances. I was told that uh, there's no scale that's more precise, that has 4 digits after the decimal point. It goes only 3 digits after the decimal point. After that, all of them are true balances, but they are
I
very
see.
expensive.
Okay, that's wonderful. Okay, so keep me posted. We can have
Yeah,
more Zoom meetings whenever you,
be great.
whenever you. But I would say that this what you already have is very, very interesting and
Thank you very much.
exciting, and it should catch the attention of people.
Yeah.
So
And I very much like your work on consciousness, and on your also your cosmology is also interesting with these playing around with these constants a bit, and yeah,
right, yeah,
yeah,
yeah.
and yeah, we can also talk about consciousness next time, and maybe black holes.
Okay,
There are many
okay.
topics to cover. Okay.
Let's do that. Very good. So thank you, and keep me posted, particularly on the support that you receive. That is important for the work to continue, I think. Yeah.
Yeah. Thank you very much.
Don't give up.
Yeah, never. Yeah, see you. Bye.
Thank you. Bye bye.